Hello everyone, I'm Jaydeep Saha and I'm representing the Electrical Machines and Drives Lab, National University of Singapore, and presenting our research on the design of integrated medium frequency transformer for dual active bridge solid state transformers or SSTs. I'll give a brief introduction, then I'll outline the dual active bridge converters and its configurations. I'll give a kind of brief on the leakage inductance design of iMFT or integrated medium frequency transformers, and I'll present the FEM simulation and experimental characterization results for the iMFT, and converter simulation and experimental results will be presented and followed by objective conclusion. So solid state transform technology has progressed significantly in the past decade and has become a competitor of LFT based solutions like transform converter unit. Now the transfer converter unit is shown here, where you have a low frequency transformer or a line frequency transformer operating at 50 hertz or whatever, and then you have a back-to-back converter over here. So the DC link over here can be used to integrate the renewables. Now, solid state transformers are multi-level isolated converters having medium frequency galvanic isolation, as you can see here, with the front end bunch of power electronics and a back end bunch of power electronics with medium frequency isolation. Here is where the medium frequency transformer comes in, and you can see there this SST is facilitated by dedicated control and communication links. So the efficiency eta and power density rho are the critical design objectives or specifications for solid state transformers, and for such superior designs in terms of efficiency and power density, a good efficiency power density design of the interbridge magnetics is quite critical. So dual active bridge converters are widely proposed for such SST architectures in all the possible configurations of DC-DC, AC-DC, and AC-DC conversion requirements. So DABs conventionally employ a medium frequency transformer and interbridge auxiliary inductor in between the two bridges, and integrated medium frequency transformer or IMFT proposed in this paper is an effort to integrate these two components together so that we can eliminate ancillary interbridge auxiliary inductor, which in turn would improve the eta rho design of the interbridge magnetics. Now coming to the dual active bridge converters, here I show the all the available combinations of DAB converters. Here it is the DC-DC DAB, here it is the AC-DC DAB, and you can see the AC-AC DAB here. Now all of them have mostly a similar kind of functional methodology or a functional modulation, that I would say. And here you can see generalized primary current and power transfer expressions, and in the power transfer you'd see a function of phi that actually controls the power transfer between the two bridges. Now, IMFT is an approach that would integrate the LS, which is critical for the power transfer over here, and it would try to integrate this leakage inductance into the MFT design. So then together we call it as an IMFT or integrated medium frequency transfer. So the IMFT's LS design is also part of the resonant transition circuitry that ensures ZVS of the semiconductor devices on the front end and the back end, that is the FE and BE semiconductor devices, and the involved current equations that shows the minimum current that is required for the ZVS facilitation of the front end and back end semiconductor devices are shown here and explained in detail in the paper. And yeah, you could see even here the LS would decide the current that could be made available for the ZVS transition. So it is quite important to do the leakage inductance design and modeling for the integrated medium frequency transformer. An approximate analytical model for the leakage inductance is expressed here. So you could see here it is a summation of constant factor here multiplied by the different magnetic energies or leakage magnetic energies. This is the leakage magnetic energy trapped in the copper volume, and the MdIW is the leakage magnetic energy in the interwinding dielectric, whereas Md primary and Md secondary respectively signify the leakage magnetic energy in the primary windings dielectric and secondary windings dielectric. Now, a modified Dowell's model can be used for estimating the leakage inductance, that is LS. So you can see here the MdIW is expressed here using this portion, and the MCU and MDX are still to be evaluated. So MCUX can be evaluated using this elaborate expression, and MDX can be elaborated using these expressions. So X can be primary or secondary as it is shown here. Now HEQX, right, for primary or secondary um, can be thought of like this or explained like this, that it is the equivalent height of the foil winding that would be constituted if we would try to convert the leads wire based design that we are using to a equivalent foil winding based design. So here we would have this denominator factor that would facilitate this conversion, and for these equations, the phi 1 and phi 2 can be expanded over here with delta as the skin depth. So all these variables and the derivation procedure is well uh, expressed and elaborated in the paper. So kindly go through them. And here our objective is to study few designs and come up with a suitable design that can um, give us integrated leakage inductance of 40 microhenry and also facilitate power transfer of 2 kilowatt, and we would like to keep 1:1 turns ratio. So here three designs are shown. First one is the conventional concentric winding based iMFT design. The second one is the non-overlapping or disjoint winding based iMFT design, and the third one is the overlapping winding based iMFT design. Now, though we do some analytical modeling, but in case of the non-overlapping or disjoint winding based design and the overlapping winding based design, the analytical model tends to show a kind of error which is more than 5%. So it's better to depend on FEM simulations for getting an accurate value before we go on and develop the prototypes. So the ANSYS FEM magnetostatic simulation results are shown here as a visualization in terms of um, the magnetic uh, energy, magnetic density or magnetic flux density. So it's expressed in Tesla. For the first conventional concentric winding, the leakage flux is quite low. For the second one, it's quite high, and the third one is intermediate. Now we go on and develop these prototypes for the three designs. This is the concentric one, this is the disjoint one, and this is the overlapping one. So when it comes to characterization, we need to do a frequency response analysis and use these two equations while doing the open circuit test and short circuit test. So we can evaluate the LM from the open circuit tests, the DC gain and the corner frequency that we obtain. And similarly, the LS can be obtained from the short circuit test, DC gain, and the corner frequency that we obtain. Now, these are the frequency responses that we obtain from the FP310 FRA, or the frequency response analyzer, and this is the short circuit test with respect to the conventional concentric IMFT design, and this is the open circuit test frequency response results. So you can see this is the DC gain that we can get, and by drawing this 20 dB per decade line, we end up with this corner frequency both for the short circuit and open circuit tests, from where we can calculate the LS and LM respectively. So we do the same thing for the non-overlapping or disjoint winding type for short circuit and open circuit frequency response, and we obtain them and get the values for LS and LM, and similarly for the overlapping winding type. So these are the tabulated results that we obtained from the analytical FEM and FRA for LS and LM. As LS is a critical design objective, so we also take help of the Wayne Carr precision magnetic analyzer, and we see there's a very good congruence and coherence between all the results. And for LM also, we do the same thing to see if there is enough magnetic flux built up. And the overlapping type of winding for the MFT design is more suitable, and we get the desired value of LS around 40 microhenry and a good um, LM, that is magnetizing inductance, and we can go ahead with it. And as I have shown in the CAD models before, we keep a consistent number of turns for all the designs for a fair comparison. Now we use this MFT and go ahead and do a simulation for a ACDC matrix based dual active bridge. These are the simulation parameters. So we do it for a 2 kilowatt converter with 400 volt DC and 450 volt peak AC, 10 microfarad of C1 and C2, that is a half bridge capacitances, and we keep the MFTs parameters constant with the characterization that we have done. So 1:1 turns ratio and 41.9 microhenry LS and 5.69 millihenry LM. We keep a switching frequency of 25 kilohertz, the AC filter inductor of 500 microhenry, and DC filter capacitor of 800 microfarad. So here we get the AC side voltage and current, and the DC side voltage and current. Then we get all these parameters with respect to voltage, VP, VS, and the current IP for the medium frequency transformer, whereas VL is the voltage that is impinged across the LS or the leakage inductance of the medium frequency transformer. We also go ahead and use the overlapping design, which gives desirable LS value with a good LM, and we use it in our MBDAB prototype so that we can do a good testing of our developed iMFT prototype. These are the obtained experimental results where we get good IAC, that is the AC current at the input, and this shows the pulse width and this shows the phase shift. So VP, VS, and IP are the various IMFT's voltage and current waveforms, and this is the DC voltage and DC current that we can see. So the IMFT's voltages and current are also zoomed in to show how the various things are operating within the IMFT, and we show it with respect to the reference of the AC and DC voltages and currents. We can see that the IMFT's waveforms are quite similar to the simulation results that we have obtained, and thus it validates our developed topology and its usefulness. So we could see that a better eta rho design of the interbridge magnetics is really needed, as DAB configurations are widely used, and an integrated IMFT can help us achieve this with a better efficiency, power density, performance for the DAB. Now, suitable analytical modeling for the IMFT is done using a modified Dawes model, and three possible plausible IMFT models are evaluated having least wire windings. There's a conventional concentric one, non-overlapping and disjoint winding based one, overlapping winding based one. We have presented the FEM simulation and hardware prototype characterization results, which are quite coherent. We have seen that the conventional concentric winding gives too low leakage, whereas the non-overlapping disjoint one gives too high leakage, whereas the overlapping winding based one gives the perfect leakage inductance that we want. And the overlapping iMFT design is simulated with a front-end half-bridge matrix-based DAB converter, and we also do a experimental validation by using the developed prototype and use it for a MBDAB converter prototypes experimentation and the validation. So thank you for your time, and if you have any doubts, I'll be very happy to answer them. If you're interested about our research, please contact us. Thank you so much.